Welcome back, everybody. This is tutorial 11 in our Learning to Use Geogebra series. So today we're going to learn how to use GeoGebra to study the properties of the derivative. So first we want to start off with motivating our need for the derivative. So why do we need the derivative? What is that concept? And so to start off, we'll just start off thinking about something a lot more familiar, and that's the slope of a linear equation. So we learned about that a couple of tutorials ago, how to make a line, how to make the slope triangle of the line. So here's the equation for the line, y equals mx plus b in slope-intercept form, where m is the slope, or the rise over the run, which is defined as y2 minus y1 divided by x2 minus x1. And it represents the rate of change of y with respect to x. So we can see in this case, when we have the slope set equal to 1, that for every change of 1 in x, our graph of our line will rise by 1. Okay? So if we change our slope to 2, we can see that our line gets steeper. And now for every change of 1 in x, our line is going to rise by 2. And so this is very useful. So one thing, a common application of this is in distance equals rate times time problems for linear equations, where the rate in one dimension is given by the speed. So if I'm driving a car and I'm going at 60 miles per hour, that's my rate of change. And so I know if I drive for 3 hours, I'm going to go a total distance of 180 miles. So that allows us to make predictions of what our distance is going to be based on how much time we drive. So the concept of rates of change show up in all kinds of math and scientific applications and is extremely important. So one nice property of a linear equation is that the slope is constant. So that rate of change does not change for the entire line. So if my slope is 2, I can take any points, y2 and y1, along that line, plug it into my equation for the slope, and I'm going to get the same value. So that's really convenient, but the problem is, in real life, there's plenty of equations that are important in applications that are not linear. So now I've plotted the parabola y equals x squared, and I asked you the question that what is the rate of change of the parabola? So does that question even make sense? And so you're probably looking at this and saying, you're more confused because the parabola does not have a constant, or doesn't appear to have a constant rate of change over the range of a function like you get for a linear equation. And to demonstrate that, let's just put a couple of points on the parabola called A and B, and let's connect them with a line. Okay, let's modify the properties of the line. So we'll change its color. We'll make it red, and we'll make it thicker so we can see it. Okay, so there's our line, and let's go ahead and put the slope triangle on this line, and we can see what the slope is. So it's 2.94. So I've taken those 2 points. So remember, for a linear equation, it doesn't matter what the 2 points are. I get the same slope, but you can see very clearly for the parabola, it's very much going to matter where I graph my 2 points. The slope is going to change. I can pretty much make it just about anything I want depending on where I put these 2 points. Well, that kind of messes up our definition for rate of change, right? So our definition of slope as a rate of change as y2 minus y1 over x2 minus x1, in the case of a parabola, doesn't make sense. It only makes sense to use 2 points and a constant slope if that slope doesn't change over the entire range of my function. And that is only going to happen for a linear equation. So for something like a parabola, that's going to, where the rate of change is going to be different depending on where I am on the graph. So down at point A now, if I make it 0, 0, it doesn't look like the function is changing very much down there, right? If I were to move away from x equals 0, the function's pretty flat at that point. But up here at point B, the function is pretty steep and it's changing. So it looks like my rate of change is different depending on which point I choose. So let's say that I want to calculate the rate of change of the function y equals x squared down here at point A. Okay, so how should that be defined? So obviously, once again, that our standard definition of slope doesn't make sense, because if I keep A fixed, the slope that I get of my line changes as a function of point B. Well, my rate of change at point A shouldn't depend at all on where my point B is, right? And it does. So obviously, our standard definition of slope is not a good definition. So what would be a good definition for the rate of change of the function y equals x squared at the point 0, 0? So I submit to you the proper definition of the rate of change of the function should be given by the tangent line to the function, in this case y equals x squared, at the point x equals a. Okay, so let's go ahead and use GeoGebra and let's get that tangent line. So we'll go ahead and get a tangent line to our parabola at point x equals 0, which is our point A in this case. Okay, so let's go ahead and modify that line so we can see it. So we'll also give it its own color. So let's make it purple, and let's increase the thickness so we can see it better. And there it is. So at point 0, we said it doesn't look like the slope is changing very much, and indeed our tangent line is completely flat, so it has a slope of 0 at that point. So that indicates that the rate of change exactly at the point x equals 0 is 0. Okay, but keep in mind, depending on where my point A is located at, that slope is going to change. Okay, so let's go ahead and move point A, and now we can see that that line changes. So let's also get a slope triangle for this line. And let's take away, for a second, this other line that we had drawn. So we can just look at the tangent line. So depending on where point A is, the slope of that tangent line is going to change. So coming down here, as I go towards positive x, the rate of change of the function is actually negative. So it's decreasing as x is increasing. And then it's decreasing, and it actually is 0 when it reaches x equals 0. And now the slope actually changes directions and becomes positive as I continue to increase x. Okay, so it looks plausible that the rate of change of our parabola at a point could be given by the tangent line. So let's actually understand why that's the case. So again, if we want to define a rate of change for a function that's not linear, where that slope can change as I change my point that I'm interested in, I have to get an instantaneous rate of change. So that means a rate of change at that point as I only go a very small distance away from that point. So why does that work? Why is that the case? Well, what we're going to do is we're going to actually zoom in on that point of interest, point A. So let's zoom in on it. And what we're going to see is that if we zoom in on it enough, and we can always zoom in on it more, you can see that this tangent line starts to approximate the function better and better. So you can see we haven't zoomed in enough here. Right around x equals 0, we're pretty good. The function doesn't change very much from our tangent line, but out here, as x is a little bit larger, we can see that our function deviates a little bit. So I don't want our function to deviate at all in our viewing window from the actual tangent line. So one more. All right, so now we've basically zoomed in enough that you can see that there's no difference between our function and the tangent line. So for any well-behaved function that has a well-defined rate of change at a given point, you can always do this. So you can always zoom in enough that there's no difference between the function at the point you're interested in and the tangent line. So here, if I'm looking for a rate of change of A, or a rate of change of the function y equals x squared at a, as I change x, as long as I change x over these small increments, and it's small enough that the function does not deviate from that tangent line, then that works. And you can see here that the slope is indeed 0. So I can increase my x over this small range, and I don't change my y at all, right? But once I get out to here, you can see that that definition is no longer good. I'll need the instantaneous rate of change of the function at that point, like 0.018, in order to maintain a proper rate of change, and it will no longer be 0 at that point. But for a equals 0, the instantaneous rate of change, as long as we're zoomed in enough and we change x by a very small amount, is going to be given by the slope of the tangent line at that point. Okay? So that's a very important concept. So let's go ahead and zoom back out. Okay, so now we've zoomed back out. So now let's just do it again to make sure that the point is clear. Let's change our point A to a different point. Let's zoom out a little bit more here so we can see our slope triangle. So now, instead of our slope being 0, you can see that our slope is close to 1 now. So at this point, let's go ahead and make it exactly 1. So at the point x equals 0.5, then the slope of our tangent line is going to be exactly 1 at that position. So let's do it again. Let's zoom in on this point and show that if we zoom in enough, that there will be no difference between our function over that very small range of x and our tangent line. And there we go. So we've zoomed in enough now. And how much we need to zoom in is always going to depend on how rapidly the function is changing its rate of change, or how much it's curving at any given position. So down at x equals 0, we've got a lot of curvature down there. So we're going to only be able to go over a much smaller range of x and keep our function equal to our tangent line. But if we go out to a steeper area that doesn't have as much curvature, you can see we have a wider range of x that we can vary and still be able to use that slope of the tangent line as a good approximation to the rate of change of our function. So you can see along this range, you can see that there's no difference that we can tell between the rate of change of our function and the slope of our tangent line. So we'll zoom back out again, and hopefully that is a good motivator to you for why the slope of the tangent line represents the proper rate of change, instantaneous rate of change of our function at a given point. And that rate of change, remember, is a function of x in its own right. It's going to be different for each different position of x that we go to if the function is not linear and it's changing its slope over that range. Okay, so now I think we motivated well that what we want for our rate of change of our function that's not linear is we want the slope of the tangent line. But now we've got a problem. How do we calculate the slope of a tangent line? So we know from our algebra that we need 2 points to calculate a slope, right? So we need 2 points. If we need 2 points to calculate a slope, but we want the slope exactly at the tangent line, then we have a problem, because our delta x, if we only have 1 point, is going to be equal to 0, right? And that's going to blow up, so that's undefined. So we can't use only 1 point. We need to have 2 points. But you can see the problem. Let's go ahead and turn on our line A again. And so what this is called, if I have it a line on a function like y equals x squared defined at 2 points, that's called a secant line. So we can see that the slope of our secant line and the slope of our tangent line are not the same, right? And again, as we showed earlier, As I change around the point B, the slope of my secant line is going to change, but my slope of my tangent line will not change as I move around the point B. Okay, so that's a key point. So how are we going to calculate slope of the tangent line? By using 2 points. So what we're going to do is we're going to move point B closer and closer to our point A. And we can move it as close as we want, but we're never going to actually let it become equal to point A. So you can see, as I turn it on and I start moving it down towards point A, you can see that its slope is becoming closer and closer to the slope of the tangent line. So we'll just continue to move it closer, and we can see that the slope of our secant line is starting to become a closer and closer approximation to the slope of our tangent line. Okay, so now for the viewpoint that we have, we still see that there's a difference between our tangent line and our secant line. So what I'm going to do is I'm going to zoom in, and so now we can't see it anymore from our slope triangles, but you can look over here on the left side of the screen and you can see our slope of our tangent line is given by m1, and the slope of our secant line is given by m, and we eventually want m to be equal to 1, okay, if it's going to have the same slope as our tangent line. So as we continue to slide point B closer to point A, you can see that our tangent line and our secant line are going to continue to get closer and closer. But the key point is I never let A and B become the same point, because at that point my denominator of my slope formula will blow up, and I can't have that. And so in mathematics, there's terminology for doing this, and that it's called taking the limit as B approaches A. So what taking the limit as B approaches A means is exactly what we're doing here. We're going to let B become as close as we want to A without actually letting them become equal to each other. So we can keep zooming in and sliding in for as much as we want, for as long as we want, but we'll never let them touch. So when we get super close, where it's hard to tell the difference between them anymore, what we'll do is we'll just zoom in some more. And now, at this point, you can no longer see any difference between our tangent line and our secant line. If we look at the slopes over here, the slopes are exactly the same. So now it no longer matters if I move B closer to point A, or even in this case, if I move it away from A a little bit. So that means that our limit has reached a fixed value. So that means as I move B closer and closer, my slope doesn't change anymore. So once that happens, I basically have the slope of the tangent line. Okay? And that's what the definition of derivative means. So derivative is basically taking the slope of a secant line and changing your second point B and making it as close as you need to get to point A until the value of the slope of our secant line doesn't change anymore. It approaches a limiting value. When it approaches a limiting value, then that slope is equal to the slope of our tangent line and represents the instantaneous rate of change of point A. And that's how we define the derivative. Okay, so I've zoomed back out now, and you can see that when I zoom back out, the points A and B are very close. They're so close now that under the zoom that I'm at, I can't tell the difference between them, and I can't tell the difference between the slope of my secant line and the slope of my tangent line anymore. So now my secant line has essentially become my tangent line because it's approached the limiting value that is the slope of that tangent line. So a nice way to think about this as well is just think of something a little bit closer to home. So think about living on the surface of the Earth. So we all know that the surface of the Earth itself is actually shaped in a sphere. But if you go outside and you're in a clear area with no buildings or anything and you look out towards the horizon, it actually looks like a plane to you. So you can't see the curvature of the Earth because you are essentially zoomed in to the surface of the Earth, essentially at a point very close on the surface of the Earth. So to you, the everything around you is essentially a plane. So you have to zoom out very far, like get in a spaceship and go out to the moon, before you can actually see the curvature of the Earth and know that you're living on a sphere. And so this is just analogous to doing that same thing, but in one less dimension. So we'll take a function like y equals x squared. We'll zoom in on a point very, 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 very close. And as we zoom in on that point, at that point, very, very, very close, and I take 2 points that are really close together, it looks like I don't live on a parabola. It looks like I live on a line. And so it's exactly the same thing. And so getting this slope of the tangent line will allow us to calculate the rate of change of our function at any given point that we want. So now I've got another graph of a parabola here, and so it's got a little bit more detail now. And so what I'm showing is I'm showing my tangent line in black here, and I've got a secant line in red, and I've got my parabola again. But this time I've defined parameters delta x and delta y. So where I like to calculate my instantaneous rate of change is at this point A. And so I'm going to call that point x comma y. And I can move that around. So the x is just whatever x location it's at, and the y is its y location. Okay? And so the other point of my secant line, point B, I want to define relative to my point A. So its x position is going to be x plus delta x. So in this case, x is 1 and delta x is 2. So my x coordinate of my point B is going to be located at x equals 3. And then I want to define my y of point B as y of point A plus delta y. Okay, so y at point A is 1 and delta y is 8. And so the y position of point B is going to be located at y equals 9. Okay, and then so I can see as I move my point B closer and closer to my point A, you can see my delta x is going to get smaller and my delta y is going to get smaller. So ordinarily you might be looking at this and being concerned. You see, if I make my point A and my point B very close together, my delta x is going to get very small, and therefore my denominator is going to, get very small. So my function, my delta y over delta x slope should blow up, right? But it doesn't in the standard case because delta y also gets small. And if delta x and delta y both shrink in such a way that I approach a limiting value as they get very close together, then I have a well-defined derivative. So in this case, I want the dy dx is my slope of my tangent line. My delta y over delta x is my slope of my secant line. So you can see, like we showed before, as I bring point B close to point A, my secant line approaches my tangent line, and the slopes get very close together. And you can see my delta x's and my delta y's shrink and get very small. So we've got to get to the point. We have to zoom in here like we did before. So I can continue making my point B become closer and closer to my point A. And I'm done. I'll be done when the two slopes are equal, or when m1 is equal to 2, the slope of my tangent line. So I'm not quite done yet. It hasn't approached its limiting value, so I haven't moved them close enough together yet. But I'm very close. So you can see about there is about good enough. So at that point, my slope of my tangent line and my secant line is the same, and the two lines are essentially equal. And so my secant line has approached a limiting value and is going to give me the slope of my tangent line. Okay? Just like we had shown before. But now as we zoom out, we can see that our slope of our secant line is 2. The slope of our tangent line is 2. And for all intents and purposes, as far as GeoGebra is concerned, the points are close enough together that there's no difference in x. Doesn't have that level of precision. Of course, we know better because we just moved them in. We know that those 2 points are not the same yet. I have not made point A and point B exactly the same, but they're very, 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 very close to each other. And so I've approached that limiting value, and I've got the value for the slope of my secant line, or the rate of change of my function y equals x squared at point A. So now what we want to do is we want to do a little bit of math to arrive at an equation for the derivative, again, that represents the instantaneous rate of change of our function at any point along our function. And so here's how we're going to proceed. So first, we're going to start off by writing the equation of the slope. So the slope of a secant line will be given by y2 minus y1 divided by x2 minus x1. And then we're going to use function notation to represent our y's. So our y2 is going to be f of x2, and our y1 is going to equal f of x1. And then if you remember, we're going to define the point at which we want to calculate the slope as x comma y. So that's what we'll call x1, y1 of our point. Okay? And then we want to define our point 2, x2 comma y2, as x plus delta x. So we want to do it relative to point x. So we got x plus delta x, and then the y will be given by y plus delta y. So using our function notation, we can rewrite our slope of our secant line as f, or as y2, which is going to be given by f of x plus delta x, because x2 is given by x plus delta x, minus f at x, because x1 is given by x. And we're going to divide that by x2, which is x plus delta x, minus x1, which is x. And that's going to simplify to give us x plus delta x minus f of x over, we can see here that the x's are going to cancel, and that'll just leave us with delta x. Okay, so at this point, all we have is we still have just the slope of the secant line. All we've done is we've just fancied the notation up a little bit, written it in function notation, and made some simplifications. So we got to add a little bit of special sauce into this in order to get the slope of the tangent line. So how do we do that? So what we're going to do is now we're going to take the limit as delta x approaches 0. Okay? And this is equivalent to taking our point B and moving it closer and closer and closer to point A until this ratio forms a limiting value, at which point in time we've got the slope of the tangent line, which we define as the derivative and write it as dy over dx. And dy over dx, or you can also write that as df over dx, represents an instantaneous rate of change of our function, or an instantaneous rate of change of y, with respect to an instantaneous rate of change of x. So that means a very small change in such a way that our tangent line represents a good approximation to our function, as we showed earlier. Okay, so that is the mathematical definition of the derivative. So let's put our definition in action. So we'll just rewrite it up here. On a couple of equations. So whenever we get some kind of new mathematics that encompasses a little bit more than what our previous mathematics did, we want to make sure that in the limiting case that our new math gives us the same results as what we would get from our old math. So what happens in the case where we take our function f of x to be equal to a constant function? So we know from algebra that if the function is constant, then it doesn't change over the range of x, and it basically represents a horizontal line. So in that case, our tangent line is constant, it's the same, and it's basically given by the slope of a horizontal line. And we know that that is 0. So what we should get for our derivative, if everything makes sense, is we should get 0. So let's go ahead and plug it in. So we've got the limit as delta x approaches 0. So our f of x plus delta x is just c, because it's a constant function, minus f of x, which is just c, over delta x. And in this case, the delta x doesn't matter because the function is constant. So we see that we'll get c minus c in the numerator, which will be 0. And as long as the points are different, we'll get a derivative of 0 for that. And so we get the expected value. So we've got a horizontal line, its slope is 0, and the derivative comes out to be 0. So far, so good. Okay, so the next case that we want to test is we want to test our function f of x equals mx plus b. So we basically want to test what is the derivative of a line. So we know that for a line, it doesn't matter which 2 points that we pick, the rate of change, or the slope, is always constant, and it's given by the value m. So when we plug it into our formula for derivative, what we should expect to get, we should expect that our derivative is going to equal m. So let's try it out and see what happens. So we've got the limit as delta x approaches 0 of m, so wherever now, this is at the point x2, so wherever we see an x, we want to plug in x plus delta x, because that's the location, the x location of our point 2, plus b minus mx plus b divided by delta x. So now we'll just do some simplification. We'll use the distributive law to get mx plus m delta x plus b minus mx minus b over delta x. So we'll do some simplification. So our mx's are going to cancel, our b's are going to cancel, and what we're left with is m delta x over delta x. The delta x's will cancel, and that'll just leave us with m. So the derivative of a linear equation is given by m. So the rate of change of a linear equation is m, which we already know from algebra, that the slope of a linear equation is constant and given by n. So that works out well. So now what we're going to do is we're going to check, we're going to do a new case now. something that we were previously unable to do with algebra. So now we're going to calculate the derivative for our function f of x equals x squared. So the example that we've been playing with all throughout this tutorial. So let's go ahead and do it. We've got the limit of delta x approaches 0 of x plus delta x squared minus x squared over delta x. So that's going to be equal to x squared plus 2x delta x plus delta x squared minus x squared over delta x. So we'll do some simplifications. So we'll see that our x squareds will cancel, and that will leave us with 2x delta x plus delta x squared divided by delta x. So now we'll cancel out the delta x, and we will get 2x plus delta x as our derivative. But, and this is where the key part comes in, we're taking the limit as delta x approaches 0. So this delta x term here gets very tiny as we take the limit of delta x approaches 0. So it can become as close to 0 as we want it to be. So this term essentially goes away in comparison to our 2x, and we're finally left with dy dx of the function x squared is equal to 2x. So now you can see this is some new math. So our rate of change of our function is itself a function of x. So at x equals 0, like we had shown before, the slope of the tangent line, or the rate of change of our function, at x equals 0 is 0. At x equals 1, it's 2. At x equals 3, it's 6. So we essentially get a linear rate of change. So the higher x gets, the rate of change of our function changes linearly with that x. And so, as you will be able to see in a more detailed course on calculus, if you actually want to calculate the derivative of x to the n, which is a more general case of x squared, then that is going to be n times x to the n minus 1. So you basically take your n, you bring it down in front of the x, and then you subtract 1 from the n in the exponent, and this will be your derivative for a general polynomial term, x to the n. So in our x squared case, we bring down the 2, bring the 2 down to the front, subtract 1 from the 2 to get the exponent of the x, and we get 2x. As we have shown. Okay, so these are just a few examples of how we actually convert all of that graphical stuff that we talked about into actual math, where we can actually calculate some derivatives of different functions using the definition that we've come up with. But remember, you know, the limit delta x approaches 0 of f of x plus delta x minus f of x over delta x might look mysterious, but there's nothing mysterious about it. So without the limit, that f of x plus delta x minus f of x over delta x is just the slope of our secant line. And when we take the limit of delta x approaches 0, we just let our 2 points of our secant line get very close together, or the second point approaching the first point, and get as close as we want until that ratio approaches a limiting value, and then that limiting value just gives us the slope of the tangent line, which is the rate of change of our function at that point. So there's nothing mysterious or magical about it. It's basically just a little bit of extensions of the principles that you learned in algebra.